For centuries, physicists have sought to understand the fundamental building blocks of the universe. Early theories focused on atoms, imagining them as tiny, indivisible spheres. However, advancements in the 20th century revealed that atoms were composed of even smaller particles like protons, neutrons, and electrons. These subatomic particles became the new focus in the quest to comprehend the universe's basic ingredients. Theories like quantum mechanics and general relativity emerged, explaining the behavior of these particles and the large-scale structure of the universe, respectively. Yet, these two pillars of modern physics seemed incompatible, clashing in their explanations of extreme environments like black holes. A new theory was needed, one that could unify these seemingly contradictory views and provide a single, elegant framework for understanding the universe at its most fundamental level. This is where string theory enters the picture. Proposed in the late 1960s, string theory offered a radical departure from traditional particle physics. Instead of point-like particles, string theory suggested that the universe is made up of tiny vibrating strings. These strings, far smaller than even the smallest subatomic particles, were proposed as the fundamental building blocks of everything we see and experience. The shift from point-like particles to one-dimensional strings may seem minor, but it has profound implications for our understanding of the universe. String theory, while still under development, has the potential to unify quantum mechanics and general relativity, offering a single, elegant explanation for the workings of the cosmos. Imagine a guitar string. When plucked, it vibrates at a specific frequency, producing a particular musical note. This simple action creates a sound that can be heard and enjoyed. In a similar way, string theory proposes that the universe is composed of tiny, vibrating strings. These strings are the fundamental building blocks of everything around us. These strings are incredibly small, far smaller than anything we can currently observe with even our most powerful microscopes. They exist at a scale that is almost unimaginable. Just like a guitar string can produce different notes depending on how it vibrates, these fundamental strings vibrate in different ways, giving rise to the different particles that make up our universe. Each vibration is unique and significant. Each vibration pattern corresponds to a unique particle with its own specific properties like mass and charge. These properties determine how particles interact with each other. For example, one type of string vibration might correspond to an electron, a fundamental particle that plays a crucial role in electricity and magnetism, while another might correspond to a quark, which is a building block of protons and neutrons found in atomic nuclei. This elegant concept provides a unified framework for understanding the diversity of particles in the universe. It brings together different particles under one overarching theory. Instead of a multitude of different point-like particles, string theory suggests that everything is made up of these fundamental strings vibrating in various modes. This idea simplifies the complex nature of particle physics. This idea has the potential to greatly simplify our understanding of the universe's building blocks. It offers a new perspective on how we view the fundamental components of matter. The concept of strings also helps address some of the challenges faced by traditional particle physics. It provides solutions to problems that have puzzled scientists for decades. For instance, the infinite densities and singularities predicted by general relativity in extreme environments like black holes become less problematic in the context of string theory. This is because strings can stretch and spread out, avoiding the infinities. The extended nature of strings, as opposed to the point-like nature of particles, helps to smooth out these infinities, offering a more consistent and comprehensive view of the universe. This makes string theory a powerful tool in modern physics. One of the most intriguing and mind-boggling aspects of string theory is its requirement for extra spatial dimensions. While we experience the world in 3 spatial dimensions, length, width, and height, string theory suggests that the universe actually exists in many more dimensions, perhaps 10 or even 11. These extra dimensions are not directly observable to us. They are thought to be tightly curled up or compactified at incredibly small scales, far beyond the reach of our current experimental capabilities. Imagine a garden hose viewed from afar. It appears as a one-dimensional line. However, up close, we can see that it has a second, curled-up dimension. Similarly, string theory proposes that our universe has extra dimensions curled up at an incredibly small scale, hidden from our everyday perception. The existence of these extra dimensions is crucial for the mathematical consistency of string theory. The equations governing string vibrations require these extra dimensions to work correctly. Without them, the theory falls apart. The geometry and configuration of these extra dimensions are thought to play a crucial role in determining the fundamental properties of our universe, such as the types of particles that exist and the forces that govern their interactions. Different compactification schemes can lead to different physical laws and constants, suggesting that our universe might be just one of many possible universes with different properties. Section 4. The music of matter: how string vibrations shape our universe. Imagine a violin string. Depending on how it vibrates, it can produce a wide range of musical notes, from low and resonant tones to high-pitched melodies. Each note is a result of the string's unique vibration pattern, creating a symphony of sounds. In a similar way, string theory proposes that the universe is a grand symphony of vibrating strings, with each vibration pattern corresponding to a different particle or force. These strings are the fundamental building blocks of everything we see around us. Just as the pitch and timbre of a musical note are determined by the frequency and amplitude of a vibrating string, the properties of a particle, such as its mass and charge, are determined by the specific way in which its corresponding string vibrates. This intricate dance of vibrations defines the essence of matter. The higher the frequency of vibration, the more energetic the particle. High-frequency vibrations correspond to particles with greater energy, much like how higher-pitched notes carry more energy in their sound waves. The amplitude of the vibration determines the particle's momentum. Larger amplitudes mean greater momentum, influencing how particles interact and move through space. This elegant concept provides a unified framework for understanding the diversity of particles in the universe. It brings together the seemingly disparate particles into a single coherent theory. Instead of a multitude of different point-like particles with seemingly arbitrary properties, string theory suggests that everything is made up of these fundamental strings, vibrating in various modes. Each mode of vibration gives rise to different particles, much like different musical notes arise from the same string. This idea of a cosmic symphony has profound implications for our understanding of the universe. It suggests a deep, underlying harmony in the fabric of reality, where everything is interconnected through these vibrating strings. It suggests that the fundamental laws of physics are akin to the rules of harmony and melody, governing the allowed vibrations of these cosmic strings. Just as music follows certain principles to create harmony, the universe follows physical laws to maintain order and structure. And just as a conductor shapes the music produced by an orchestra, the geometry and configuration of the extra dimensions in string theory determine the allowed vibration patterns of the strings, ultimately shaping the properties of our universe. These extra dimensions are like the unseen hands of the conductor, guiding the cosmic symphony. Section 5. The Cosmic Symphony. Different string vibrations, different particles. One of the most remarkable features of string theory is its ability to account for the vast diversity of particles in the universe through the different vibrational modes of strings. This theory provides a unified framework that elegantly explains the existence of various particles. Just as a single guitar string can produce a variety of notes by vibrating at different frequencies, a single type of string in string theory can give rise to a multitude of particles. Each particle corresponds to a unique vibrational pattern, much like each note corresponds to a specific frequency on a guitar string. For instance, one particular vibrational mode might correspond to an electron, with its specific mass, charge, and spin. This vibrational pattern is what gives the electron its unique properties, distinguishing it from other particles. Another vibrational mode might correspond to a quark, another fundamental particle with its own unique properties. Quarks, which combine to form protons and neutrons, have their distinct characteristics defined by their specific vibrational patterns. The entire spectrum of particles in the standard model of particle physics, including photons, gluons, and neutrinos, can be represented by different vibrational patterns of these fundamental strings. Each particle's unique properties are a direct result of its specific vibrational mode. This concept provides a beautiful and elegant explanation for the diversity of matter in the universe. It unifies the seemingly disparate particles into a single framework, showing that they are all manifestations of the same fundamental strings. Instead of a multitude of different fundamental particles, string theory suggests that everything is made up of these fundamental strings vibrating in various modes. This idea simplifies our understanding of the universe's building blocks. The specific properties of each particle are then determined by its unique vibrational pattern. These patterns are like the fingerprints of particles, defining their identity and behavior in the universe. This idea of a cosmic symphony has profound implications for our understanding of the universe. It suggests that the universe is a harmonious entity, with each particle playing its part in the grand symphony of existence. It suggests that the fundamental laws of physics are akin to the rules of harmony and melody, governing the allowed vibrations of these cosmic strings. These laws ensure that the universe remains in a state of balance and order, and just as a conductor shapes the music produced by an orchestra, the geometry and configuration of the extra dimensions in string theory determine the allowed vibration patterns of the strings. These extra dimensions ultimately shape the properties of our universe, guiding the symphony of particles and forces that we observe.